Okay, so radicals are anything that has a square root, cube root, fourth root. So we can say that the power on the outside is called the root. The inside is called the radicand, and the symbol is called the radical. Okay, so we have to make sure that we know all of our perfect squares, perfect cubes, perfect fourths, etc., either by memory or whenever you write a test or a quiz, writing them down the side is a good strategy to recall them quickly. So let's just quickly fill in a chart. We've got 1 times 1 is 1, 2 times 2 is 4, 9, 16, 25, 36, etc. Make sure that these should hopefully already be memorized for you from grade 8 and 9. And the perfect cubes, we have 1 times 1 times 1, which is 1. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. 64, 125, and 216. And our perfect fourths are 1, 16, 81, I'll let you figure that one out, and 625. And our perfect fifths, again, 1 is always 1, 32, and 343. Okay, so hopefully you figured out 4 to the power 4 is 256. Okay, so in grade 11 pre-cal, we have to do a lot of calculations without a calculator. So we need to look at these cube roots in example 1 and figure these out without a calculator. And that's why it's important that you memorize your roots. So if we look at the cube root of 216, we know, well, 216 is 6 times 6 times 6. So if we cube rooting it, find out what we started with, it would be 6. And why is that? Well, the cube root of 216 is equal to the cube root of 6 times 6 times 6. And notice there's 3 6's, and there's a 3 on the outside. That means when we cube root it, we're just left with the 1 6. Okay, if you look at the fourth root of 16, so the fourth root of 16 would be 2. And you can kind of think of it as like tree roots, because we're thinking of what was the root that we started with to get 16. So we said 2 times 2 times 2 times 2. There's 4 of them. When we fourth root it, we would just want to know what was the initial number that we had at the beginning. So it's 2. Okay. Fourth root of 256. If we go to our chart, the fourth root of 256 is 4. The fifth root of negative 32. Now, because it's a fifth root, it's an odd power. And whenever we have an odd number of negatives, our answer is always negative. And so the fifth root of negative 32 is negative 2. And you can check that. You can always check your answer because we know it's the fifth root. So negative 2 times negative 2 times negative 2 times negative 2 times negative 2 should equal negative 32. Now D looks a little bit different because we have a variable instead of a constant. So when we have x squared, what we can do is we can write it as x times x, and it's just like all of the examples above, right? We had 4 2's, so when we take the fourth root, we just get the single 2. When we have 2 x's and we take the square root, our answer is x. Another way of writing this is using an exponent to write it. So remember that when you're writing a radical as an exponent, it would be 2 over 2, which also equals x, or x to the 1. Alright, so for m, let's try using exponents as well. Remember, the number on the bottom is always on the outside of the radical, and the number on the inside is on the top. Okay, so this would equal m squared. Or we could have written this as the square root of m to the 4 times m to the 4, fourth rooted. And because we have 1 here and 1 here that both have a power of 4, we would get m squared. Okay. It's generally a little less confusing if you use exponents to simplify. So in this case, remember the denominator of our fraction is 5, and the numerator is 20. So our answer would be k to the 4. And last but not least, h is the cube root of negative 27n cubed. So let's actually do this in two parts. So the cube root of 27 we'll talk about first. So the cube root of negative 27 would be negative 3. And you can check your chart. The cube root of 27 is 3. And the cube root of n cubed would be n to the 3 over 3. So our final answer is negative 3n. Again, there's an imaginary 1 beside the n, but you don't have to put that. Okay, so now let's look at how we can use that knowledge and simplify some radicals. Okay, and when we say simplify, that means we want to evaluate it as much as possible without a calculator. So if we look at the first one, we have the square root 50. So we need to find a perfect square that multiplies to 50, okay? And so I'm going to start actually by writing all my perfect squares down the side. So I have 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared. And this is a good thing to do on the front of a quiz or a test, just so you have a reminder on the side, because you will not be able to use a calculator. Okay, so if we look at the first one, we have 50. Now, I know that 1 goes into 50, but that's not going to really help me. So let's start at the largest number and work our way backwards. So 100 does not go into 50. I think the next one that goes into 50 would be 49, but it doesn't multiply to 50. 36 also doesn't multiply to 50, but 25 does. So I can rewrite this as the square root of 25 times 2. And because we are allowed in math to split up the product of a radical, we can split it up as follows. And the square root of 25 we know is 5. The square root of 2 we don't know. It's a decimal number, so we just place it after. Now, because they're multiplying, we need to put them back to back. You could write the dot in between, but you don't have to. All right, example B. What multiplies to 80? And the reason I start with the largest number is because that way I won't have to repeat steps. So let's see if we can figure out what goes into 80. Now, I don't think 49 does, 36 doesn't, and the way to check is to take your calculator and just type in 80 and see if it is divisible by these numbers. So if we try 80 divided by 36, we get not a very nice number. So let's try 80 divided by 25. Don't think so. No, also a decimal. So 80 divided by 16 is 5. Now, if you're not allowed to use a calculator, then you're going to have to do a little bit of long division or scratch work on the side. But we know that this is 16 times 5. Okay, and again, we can split that up. Root 16 times root 5, and the square root of 16 is 4, square root of 5. All right, 63 is 9 times 7, and the square root of 9 is 3, and the square root of 7 we don't know without a calculator. We can estimate, but we can't find accurately what it is. And the square root of 7 we call an exact value, because if we were to type in the square root of 7 into our calculator, we would get a very long or maybe a short decimal number, and it wouldn't be exact. When you leave a number as a square root, that is called an exact value. All right, so D is slightly different. D already has a number on the outside. So what we're going to do is we're just going to ignore it. We're going to keep it there during every step, and we're going to pretend it's not there. So square root of 18, I know is 9 times 2. So let's write that 9 times 2. And it is good to remember that this 5 in front of that is also multiplying everything. So we have 5 times, well, the square root of 9 is 3. And I don't know what the square root of 2 is. So my final answer would be 15 square root 2. Okay. E and F are for you to figure out on your own. All right, example 3. We have now variables instead of constants. So the nicest thing to do is to rewrite it either as an exponent or break it apart. So in this case, we have a square root, so there's an imaginary 2 there that we don't really write. And x to the 7 we can write as x times x. We could write it like this, it's a little bit of work, and find how many groups of 2 we have. So this would equal x cubed, because I have 3 groups of 2, and I have 1 square root left. Or we could also write it as the square root of x squared times x squared times x squared with 1 left over, which also equals x cubed, because there's 3 of them, times the square root of x. Or, this is my preferred method, is we write it with an exponent. So we have 7, and remember the number in the bottom of your fraction is always the outside root. It's the nth root. So in this case it's the square root, so I have 7 over 2. So in this case I would get x to the 3, and I have x to the 1/2 left over, right? I've got 2 goes into 7 3 times, and I have 1/2 left over. And another way of writing that is x cubed times the square root of x. So whichever method you like, totally up to you. Alright, so b, we're finding the cube root of a to the 6, b to the 10. So this one, let's rewrite it. We have a to the 3 times a to the 3 times b to the 3 times b to the 3 times b to the 3. Remember, you add exponents when they have the same base. So we have 3 plus 3 is 6, which is what we started with. And we have 3 plus 3 plus 3 is 9, so I need 1 more. And so what I can do is I can say I have 1, 2 of the a cubes, and remember the 3's, that allows us to remove the root. So we have a times a times b times b times b, and we have 1 cube root of b left over. And if you simplify, we have a squared times b cubed times the cube root of b. Okay, so in C, it looks slightly different because there's a constant and there's 2 variables. But luckily for us, we know what the square root of 36 is. The square root of 36 is 6. C to the 4, we can rewrite as c squared times c squared, and d squared can remain at the end. And then we have 2 of these c squareds that are going to cancel out with the square root. So we have c squared and d squared left inside. And luckily, we can also take the square root of d squared and get d. We just have 1 square root or square that will cancel with the square root. Okay, d. Square root of 20, let's see if we can break apart. So I would say that's 4 times 5. G to the 2 times g to the 2 times g2, g2. And then h, instead of writing it out 16 or 8 times the square, I'm going to say this is h to the 16 times h. And so let's break it apart piece by piece. So the square root of 4 is 2. I don't know what the square root of 5 is. And then I have 1, 2, 3, 4 g squareds. And if I take the square root of a square, I just get g 4 times. And then h to the 16 would be h to the 8. And I have root h left over. Okay, and E and F I will let you try on your own. Okay, so that's how you simplify a radical. Now, if we wanted to go the other direction, we have to put our constant or our variable that we evaluated from the root back underneath the square root or cube root or fourth root, etc. So what we want to do is we're going to write a whole root. The 13 will stay inside. And we're going to bring the 2 back inside, but it was a 2 on the outside. When we bring it under the root, it becomes the square root of 2. And we don't want to change the value of this expression. So because it's a square root, we're going to square it when we bring it inside. So our answer would be 13 times 4 square rooted. So the answer would be square root 52. Okay, so for B, we have a cube root, which means when we take our 4 and bring it inside, we need to cube it to undo that operation of bringing it inside. We still want it to equal the whole number 4, and because we're bringing it inside and cubing it, the cube root of a cube would just give us the value of 4 again. And so we just have to simplify. We have negative 5 times 64. Which is equal to the cube root of negative 320. Okay. For C, again, we put the root B stays inside, and this time it might be better to use brackets because you have two parts of your term, and we're going to square the whole thing because we brought 2b inside, so we need to square it. So our answer would be b times 4b squared. Don't forget to square both of these values, which equals the square root of 4b cubed. Okay, and I'm going to let you try D by yourself. Alright, last example. Last example, it says arrange the following radicals from least to greatest. So notice all of them are square roots except for 13, which we'll deal with in a sec. But let's take them each individually. So square root 49 is fine. It's a square root. We know what it looks like. 13, we need to change to a square root so we can kind of compare it to everything else. So if I take 13 and I put it underneath the square root, remember when you put something underneath the square root, you have to square it. So this would be the square root of 169. And the reason we change them all to entire radicals is so we can easily say, okay, well the square root of 149 is definitely smaller than the square root of 169. Okay, so for this one, 4 square root 10, we're going to keep the 10 inside, and when we bring the 4 underneath the root, we square it. So this becomes the square root of 160. This one, let's rewrite. The 42 to 1/2 is the same as writing the square root of 42. So we'll just do that first. And then 42, when we bring the 2 underneath the square root, we square it. This is like saying 42 times 4. So we have the square root of 168. And last but not least, we have the square root of 19 times 3 squared, which is the square root of 171. So now we can easily say which is the smallest and which is the largest. So this is the smallest,